Differential equations describe dynamical processes such as climate change or the movement of robotic arms. To find them, scientists rely on the scientific method, which has led to significant technological advances. However, the scientific method is hypothesis-driven and hence prone to human biases. To overcome these biases, researchers seek ways to extract differential equations with data-driven approaches, which can be free from tricks played by the human mind. Such methods could quickly identify the equations governing the movement of industrial robots, enabling the data-driven modeling of production processes. Digital twins could help us find multi-scale and multi-physics engineering solutions to complex challenges such as aeroplane design. Supervised learning algorithms predicting drug performance in time could be combined with unsupervised learning methods to generate new drug compounds automatically. We could characterize the behavior of soft tissues and describe cell behavior and biomechanics purely from data. The impact of extracting differential equations from data is potentially vast. It would enable scientists to identify promising phenomena, deliver rapid analysis, and quickly interpret discoveries. Models that would otherwise take years to identify could be extracted almost instantaneously, allowing scientists to focus on deciding whether the models matter. In 2016, Stephen Brunton, Joshua Proctor, and Nathan Kutz, all at the University of Washington in Seattle, published a paper in PNAS detailing a sparse regression method to extract differential equations from data. Given a library of candidate linear and nonlinear basis functions, the goal is to infer a nonlinear model from time series measurements that correctly identifies the underlying dynamics. A key assumption is that the true differential equation is comprised of only a few terms, making the model sparse in the space of the basis functions. Applying ordinary least squares would return as many coefficients as the number of basis functions we started with. Hence, we need sparse regression methods. In their 2016 PNAS paper, Brunton, Proctor, and Kutz present a sequential thresholded least squares algorithm. They use a library of monomials to fit a chaotic Lorentz system and the PDEs for vortex shedding behind the cylinder. The researchers developed PySINDy, a software package in Python for the sparse identification of nonlinear dynamics from data. In our group, we then coded Seed, a Python wrapper around PySINDy. Seed has a simple and intuitive graphical user interface so that researchers in a wide variety of fields can use the cutting-edge methods of PySINDy without needing to know any programming.